Okay, Chemistry 3202, course overview, review. What we're going to look at today is Lesson 4, Unit 2, Section 1, Lesson 4, Writing Bronsted-Lowry Equations. Now this is a very, very important lesson. I'm going to do several examples here. One of these questions almost always shows up in the long answers of the public exam. So it's going to be very important that you know how to do a Bronsted-Lowry equation. So here we go. Okay, this is dealt with on page 562 of your textbook. Here are the outcomes for this lesson. Okay, the very first thing we're going to do is we're going to do a little review of Chemistry 2202. We're going to look at net ionic equations, and we want to be able to look at chemical reactions, and we want to be able to try and remove any species in the reaction that's really not doing anything that's going to be a spectator, that their only purpose in being in the reaction in the first place is to bring some other ion or species along with it, all right, so that it could dissolve in water. And then all of a sudden, once it's dissolved in water, it's just floating around in the water and it doesn't do anything else. So we would refer to that as spectator. So we want to be able to get rid of all this riffraff, I guess you can call them, and we want to be able to see what's going on in the chemical reaction. So here's an example of what we can look at. We can take a reaction of silver nitrate with potassium chloride, and we want to be able to write a total equation here. And we're going to see that silver nitrate reacts with potassium chloride, and it's just a double replacement reaction where the two metals, the silver and the potassium, simply swap places here. So what we end up with on the other side is going to be silver chloride and potassium nitrate. All right. Now we want to be able to write these in their chemical formulas. So here we go. So silver nitrate, AgNO3, potassium chloride, KCl, silver chloride, AgCl, and potassium nitrate, AQ. Now, you notice here I've got the subscript changed here. These guys were both aqueous solutions. Well, recall that if we had to look at this particular reaction, we'd notice that when we mix these two together, we would end up seeing a white precipitate sinking to the bottom. And if you check your solubility tables for chloride, you notice that silver compounds with chloride would be insoluble, so they would precipitate as a solid. Okay, there we go. All right, so we've got our total non-ionic equation. Good enough. We can see what's causing the white precipitate. So what we do then is we would say, okay, anything in this equation that's aqueous, AQ, really they're going to be dissociated to form ions. So silver nitrate really exists in the aqueous state in its dissociated form. It's going to be silver ions and nitrate ions. Likewise, potassium chloride. We will not be able to dissociate silver chloride because it's stuck together to form silver chloride crystals here. So these guys are going to be taken out of the solution. So we have to leave these guys as they are, and we'll dissociate the potassium nitrate into its ions. So our total ionic equation would look something like this, okay, where everything that was AQ now is written in their ionic form, except for the silver chloride, which is in the solid state now. What we're going to do next is we're going to say, all right, let's cross out any spectators. Anything that really doesn't change in this chemical reaction is really not involved in the overall reaction. So we're looking at this and we're saying, well, the nitrates don't change. The potassium doesn't change. The only thing that really changes is the silver ions react to form an ionic compound, silver chloride. So the silver ions have changed. And likewise, the chloride ions now react with the silver, and the chloride ions change. So once we cross out our spectators, what we're left with is the overall reaction of what's actually happening in that test tube. That's very important. The important thing that's happening in this test tube is that silver ions react with chloride ions to produce silver chloride. So we got rid of the riffraff. We don't need to see these guys because they're not involved in the reaction. The only purpose that nitrate served was to bring silver into the game. The only purpose that the the potassium served was to bring chloride into the game. On this side of the table, their only purpose is to try and make everything electrically neutral. All right, and that's it. They don't do anything else. So this is what we want to look at. So that's what this is called, a net ionic equation. All right. We want to relate this now to acid-base reactions. And there's a 5-step method for writing Bronsted-Lowry equations. And I'm going to call it the no-fail-Wells method. All right, you can call it whatever you want to call it. But it's simply a 5-step algorithm or a method that we're going to use to try and write these net ionic equations for acid-base reactions. Now, I'm going to go through these, and I'm going to do an example as we do. The very first thing we have to do is we have to start listing all the species that are going to be mixed together in the test tube or the container or the reaction vessel. And once we list everything that's mixed in there, we have to look at it and say, okay, here's a typical reaction. All right, we're going to rate the reaction of sodium hydroxide with hydrochloric acid. So these are the two things that are going to be mixed together in our container. So let's go back. And we're saying, now that we've listed all the species present, we got to look at them and say, well, how is it going to behave? And there's a number of ways that these compounds can behave. And the first thing we can say, well, what if it's an ionic compound? So if it's something like, say, sodium bicarbonate or sodium hydroxide or potassium nitrate or things like that, these guys are ionic compounds, metal and a complex ion. These guys are really going to exist as sodium ions and bicarbonate ions. So when I look at my example over here, I'm saying, hey, look at that. That's an ionic compound. So really, sodium hydroxide is going to be existing as 100% dissociated. So in this test tube, we're really going to have sodium ions floating around and hydroxide ions floating around. Okay, let's go back. Okay, what other types of roles can these molecules have? Well, we can identify something as a strong acid. And we know it's a strong acid because we have our acid-base table, remember. And if it's a strong acid, it's going to be one of these guys on the top here because they're 100% ionized. So we got to look at the acid and say if it fits here, then it's going to be 100% ionized. If it's 100% ionized, then that's what it exists as. If it's one of these acids down here, then it doesn't really want to break down. So let's go back and look at what we got here. Okay, the other thing we can look at, okay, if it's a strong acid, something like hydrochloric acid, then it's going to be 100% forward. All right? And in this case, hydrochloric acid really doesn't exist like this because that doesn't exist anymore. As soon as that hits the water, it's going to exist as H3O plus and Cl minus. The other example, of course, if it's a weak acid, then it's going to exist, it doesn't want to break down. It wants to stay as it is. So something like acetic acid, we don't do anything with it. It doesn't want to. It only wants to break down 1% of the time. 99% of this stuff stays as it is. So what we do is we simply leave it as it is. We don't do anything with it. And then finally, water is always going to be present in every single chemical reaction that we're doing for acids and bases, for the most part, because we're dealing with aqueous solutions. And we know that water is this amphoteric species that can be an acid or a base. So therefore, we have to include it in all of our overall overview because we know it's there and it can exist as an acid or it can exist as a base. So we're looking at the next thing here, and we're saying, okay, hydrochloric acid, we're throwing some hydrochloric acid in the test tube. As soon as that hits the test tube, hits the water, what's going to happen is we've identified that, hey, that's a strong acid. That's one of those way up on top of the table. It's not going to exist as HCl. It's really going to exist as H3O plus and Cl minus. So there we go. We've listed the species that are going to be present in this test tube. Okay, there we go. So that's all the species that are going to be present when we mix them together, assuming nothing has happened yet. All right, so that's step 1 done. Step 2. Okay, once we look at step 2, we're going to have to use our acid-base table to identify what substances can exist as an acid and which substances can exist as bases. So we're going to look at our list here that we've got written out, and we're going to say, all right, let's do the acids first. Sodium cannot be an acid because it doesn't have any hydrogen to donate, so it's not an acid. OH minus, that can be an acid. H3O plus can be an acid. Chloride, no hydrogen, not an acid. and water can be an acid. So here we are, we're faced with a dilemma. We've got 3 possible acids in this test tube. Which one is going to act as the acid? Well, we're going to deal with that now in a second. Let's identify the bases. Sodium can accept the hydrogen? Not really. All right, it's not going to be a base. Let's check our table anyways to see if sodium is on the table. So we go to our table and we're looking for sodium. And no sodium. So sodium cannot be an acid, nor can it be a base. It's going to be one of these spectators. In an acid-base reaction, sodium is generally a spectator. Hydroxide? Absolutely, that's a base. That's going to be from sodium hydroxide. H3O+? No, that's not going to be a base. You can't get any more hydrogens there. And this guy here can be a base, and water can be a base. Let's check our table. And I'm looking at these guys and I'm saying, well, look at this. There's my hydroxide ion. Okay, there's water as a base. And what was the other one? Chloride, right there. So that's my 3 bases. Okay, so we can find these species on the table. So that's part 2 done. So that's already got me a couple marks on my public exam, just because I did that. All right, now that we've identified which one is which is acids and which is bases, we have to identify the strongest ones. Whichever one is the strongest acid, that's the one that's going to be the acid. Whichever one's the strongest base, that's the one that's going to be the base. And then we're going to write our reaction. So if we're looking at this and we're saying, okay, OH minus, H3O plus, H2O, which is the strongest acid? I go to my table. I'm looking at these guys and I'm seeing H2O is on the bottom. H3O plus, there it is. All right, remember now these guys don't really exist like this. These guys exist like that because they're strong acids. All right, there's H3O plus, so that's really strong. H2O, and what was the other one? Well, that's it. Well, we know H3O plus is going to be the strongest acid. There it is. So I'm simply going to go over here and I'm going to put a little green box around H3O plus. There it is. That's my strongest acid. Now I'm going to go look at my table for my bases, and I think we've already established from our base that OH minus is the one that's lowest on the table. Right? There's Cl minus, there's water, and OH minus is way down here. Very strong base, very strong base. OH minus is on the acid side, but that's a very weak acid, right? So OH minus, the strongest base. So let's go back and look at it. There we go. This guy's the strongest base. So now I know what my reaction is going to be with. I'm going to have a reaction of H3O plus with OH minus, and I'm looking at this and I'm saying, all right, the H3O plus is acting as my acid. The OH minus is acting as my base. So that's the transfer there. The water now obviously is going to be the conjugate acid and the conjugate base. It's going to behave as both. Okay? Now the question is this going to be a one-way reaction or is it going to be two-way? And I think I went too quickly here, but in any case, we simply wrote the reaction using the strongest acid and the strongest base. What we need to do here in part 4 is determine whether or not we're going to have a single arrow or a double arrow. And we're saying that, okay, this is easy enough. It's going to be a single arrow, stoichiometric, meaning 100% forward, if we have hydronium and bases stronger than nitrite. Now what are they talking about there? Hydronium and bases stronger than nitrite. Well, let's go to our table. And I'm looking at my table and I'm saying, okay, if I have hydronium and bases stronger than nitrite, there's nitrite. They have a line drawn in the table. Any one of the bases that's stronger than nitrite is going to be 100% reacted with H3O+. So when you have a strong acid, H3O+, reacting with any one of these bases, we're going to have a single arrow. It's going to be 100% forward. And what that means is that each of these bases is sufficiently strong enough to accept the hydrogen from H3O+. If these bases are above nitrite, then these bases are too weak to accept a hydrogen. They're not going to do it, and as a result, we're going to get some reversible reaction happening here. Okay, so let's have a look at it. Okay, and then finally we're saying, all right, it's going to be non-stoichiometric, we said, if we have a weak acid with a weak base, or hydronium with bases weaker than fluoride. We just talked about that, or hydroxide with acids weaker than sulfite. So we never talked about hydroxide. We said if we have hydroxide present, that's going to be 100% forward if we have acids stronger than hypochlorous. So if we look at our table here, okay, there's hypochlorous acid. We said hydroxide with any of these really strong acids. These acids now are strong enough to donate their hydrogens. If we have hydroxide with those guys, 100%. Hydroxide with any of these guys down here, these acids are not strong enough. They don't want to give away their hydrogens. It's going to be non-stoichiometric. Okay, so there we go. Now, we're looking at this particular reaction. We're saying, okay, H3O plus is a strong acid. OH minus is one of these strong bases. So this is going to be 100% forward. There we go. Let's look at another reaction here now. Okay, here's an equation for the acid-base reaction between nitrous acid and sodium sulfite. All right, so I'm looking at these guys and I'm saying nitrous acid, nitrous acid, nitrous acid. I check my table and I find out that nitrous acid is a weak acid. So because it's a weak acid, I can say, yeah, we'll leave it as it is. Doesn't want to break down. Stays as it is. 90% of that stuff doesn't want to do anything. Sodium sulfite, that's sodium sulfite. That's an ionic compound, sodium and a complex ion. So this guy's going to be 100% dissociated. There we go. It's going to break down into sodium ions and sulfite ions. What I want to do now is list all the species present. So there we go. We've got nitrous acid, I've got sodium ions, I've got sulfite ions, and I got water. I want to list which ones are acids and which ones are bases. So nitrous acid, clearly an acid when it's weak. Sodium cannot be an acid. Sulfite cannot be an acid. Water can be an acid. I go and list, I look at my table now, which ones can be bases. Nitrous acid cannot be, sodium cannot be. I find sulfite on my table on the base side. There we go. I find water on my table on the base side. So water can be a base or an acid. Now what I have to do is decide which of these acids is the strongest. And when you check your table, you'll see that HNO2, even though it's a weak acid, it's stronger than water. And likewise, for the bases, even though SO3 2- is not a real strong base, it's stronger than water. So that's my two species that I'm going to use in my net ionic equation. So there we go. We get something like this. And we see that HNO2 is acting as the acid. SO3 2- is acting as the base. So we get the transfer that way. This guy now is going to be my conjugate base, and this one's going to be my conjugate acid. The nitrates go together. There we go. Now we have to determine the stoichiometry here. And the stoichiometry simply said, you know, remember what we said? Let me just go back here. And we said, if we had H3O plus with a base stronger than nitrate, or OH minus and an acid stronger than hypochlorous, then it's going to be single arrow. Here's what we're looking at. We don't have H3O plus, we don't have OH minus. We have a weak acid, nitrous acid, and we got a weak base, the SO3 2-. So this guy's going to be non-stoichiometric. We're going to have a double arrow because this reaction doesn't really want to go forward that much. So double arrow. Okay, it's a mixture of a weak acid and a weak base, therefore it's going to be non-stoichiometric. It's going to be not 100% forward. And now we want to say, okay, are the products going to be favored or are the reactants going to be favored? Is this reaction going to push forward to produce more products, or is this reaction going to stay on the reactant side and end up being more reactants? And what we have to do here, it's step 5, and we're saying we have to consider the strength of the acids. We're comparing the acids. The acid and the conjugate acid. So that's a very important point. We're going to compare the strength of the acids. Okay, I'm not comparing what I'm mixing together. I'm comparing the strength of the two acids in the overall equation. And what we're saying then is if the acid is stronger than the conjugate acid, then the equilibrium lies to the right. Okay, so this is what we're saying then, is if the acid is stronger, greater than the conjugate acid, look at the arrow, then the equilibrium is going to push that way. K is going to be greater than 1. If the conjugate acid is weaker than, if the conjugate acid is stronger, watch the arrows now. If the conjugate acid is stronger, higher on the table, then look at the way the arrow points. We're going to be going in that direction. K is less than 1. The reactants are favored. So let's look at our particular example here. We want to compare the acid with the conjugate acid. We're comparing the strengths of the two acids. Which acid wants to break down? So what we have to do is we have to check our table. So HNO2 and HSO3. So if I'm looking at my table right here, HNO2 is right up here. There's HNO2. I'll do it in purple. There's nitrous acid and HSO3. HSO3. You have a job to see them here. Right here. So which is the stronger acid? Nitrous acid. So I go back to my problem and I'm looking at this and I'm saying, okay, I'm going to compare my weak acids, my acid and my conjugate acid, and we're saying then that HNO2 is higher on the table, so HNO2 is greater than or stronger than HSO3 minus. So therefore, the reaction is going to proceed in the forward direction. You notice how I've got done with the arrows here? I've got the forward one drawn a little bit bigger than the reverse one, indicating that the equilibrium is favoring the forward direction. Because this acid wants to break down a little more than this acid. So the forward reaction is going to happen before the reverse one would. There we go. Let's try another one. Okay, here's a reaction between hydrochloric acid and aqueous sodium sulfide. I'm going to leave it up to you guys now to look up the tables. Hydrochloric acid, that's one of those strong acids. It's right up on the top. So as soon as we identify this as a strong acid, we're saying, hey, hydrochloric acid doesn't exist as HCl. It really exists as H3O plus and Cl minus, right? It reacts with the water instantly 100%. So HCl really doesn't exist. It exists as H3O plus and Cl minus. I'm looking at sodium sulfide. That's an ionic compound, sodium with an ion sulfide. And we're saying that's 100% dissociated because it's ionic. So my species present, I list them. Don't forget to include water. I have to look at my table here now to figure out which ones are acids and which ones were bases. Well, I know H3O plus is an acid and water is an acid. I look at my table for bases and I can see that Cl minus is on the base side, sulfide is on the base side, and so is water. I have to figure out which one is the strongest. The strongest acid is the highest one, H3O plus. The strongest base is going to be the lowest one. S2 minus is the strongest base now. So that's my two species that are involved in the reaction. Okay, I write them out. H3O plus acting as an acid, S2 minus acting as a base. There's my conjugate acid, conjugate base. Now I've already got this put in as 100%, but what we have to do is say, okay, look at rule number 4. Rule number 4 says H3O plus with any acid stronger or above that line. So let's go and see where that locates. So H3O plus with any base below this line. So where does the sulfate ion? Oh, there's sulfite right there, look. So sulfite is sufficiently strong enough to cause a 100% reaction with H3O plus. So because of that, we know that this is a stoichiometric reaction. As soon as the sulfite hits that solution, it's going to instantly accept the hydrogen. It's strong enough to accept them. And there we go. So we want to look at the horizontal line, and in other words, we're saying S2- is strong enough to accept every single hydrogen, and therefore it's going to push forward 100%. This acid here is so strong, this guy is just a weakling by comparison. It's not going to want to be able to reverse. No way. It's too weak. This one is just way too strong. So the forward reaction is dominant. Okay, here's another one. We're going to take some sodium hydroxide and mix it up with some sodium bicarbonate. You might say, well, sodium in both reactants? Yep, because sodium is going to be a spectator. Its only job is to bring these other acids and bases into the reaction. So I'm looking at sodium hydroxide, and I'm saying, yep, that's ionic because it's sodium. Dissociates 100%. Sodium bicarbonate, well, sure, that's ionic too because of the sodium, metal in a complex ion. There we go. Species present, we don't have to write sodium twice, right? It's there. It's going to do the same thing no matter which one you have. And again, don't forget the water because water is always present. We list our acids. That can be an acid, but it's a very weak acid. That can be an acid, and that can be an acid. The bases, sodium doesn't do anything. It's a spectator. Hydroxide is a strong base. Bicarbonate is a base. Water is a base. All right, look up your tables. The strongest acid from the list is HCO3-. The strongest base of the three is going to be OH-. All right, again, check your tables. The chemical reaction here, bicarbonate acting as an acid, hydroxide acting as a base. So we're going to see the transfer of the hydrogen that way. And what we end up with is carbonate and H2O. Okay, we have to determine what this is going to be right here. And we're saying, okay, we got OH-. That's one of those special ones. OH- is a strong base. So what does that mean for us? Well, let's go look at our table. We said anytime we have OH- and an acid that's stronger or above this line, it's good to go. It's going to be 100% forward. Anything that's below this line is going to be too weak. And what did we have again? We had OH- and bicarbonate. OH- and bicarbonate. There's bicarbonate right there. So bicarbonate is not a strong enough acid to want to completely and totally react with the base. So it's going to be non-stoichiometric. And now that it's non-stoichiometric, we have to figure out what is... Okay, we have to determine the position of the equilibrium now. Is the forward reaction going to be favored or the reverse reaction? And again, what we do in order to compare, we have to compare the acids. And we're looking at this, and right away we should know the answers because water is a very, very weak acid. So what we're saying then is that bicarbonate is a much stronger acid. It's greater than water. It's higher on the table. Therefore, the reaction is going to push forward. This acid is going to give up its hydrogen much more easily than that one there. So the reaction is going to push forward. So again, I would write my arrows slightly bigger in the forward direction. There we go. Okay, one more example. Number 5 here. Sodium hydroxide is used to neutralize vinegar. We're looking at this sodium hydroxide, ionic compound, sodium and a complex ion, made of ions. So we dissociate that 100%. Vinegar. Now, vinegar, acetic acid, is a weak acid. It's only 1% dissociated. Check your table on that. So because it's a weak acid, we're going to leave it as it is. It tends not to want to ionize. In other words, when I put vinegar in this mixture with water, only 1% of it really wants to go forward. The other 98% wants to stay like it is. And that's why we leave it as it is, because it's a weak acid. This reaction really does not want to go forward. It wants to go backwards. So that's why we leave weak acids as they are. Okay, we list the species present. So in this case, we've got some sodium ions, hydroxide ions, we've got some acetic acid molecules, and we also include water here. We need to list the species as acids and bases. So again, check your table. Hydroxide can be an acid. Acetic acid can be an acid. There's the acidic hydrogen on the carboxylic acid group. And water can be acidic as well. The bases, sodium's being spectator, and water is a base. Which is the strongest acid? It's going to have to be acetic. Check your table. Your strongest base is hydroxide. We write our equation. There we go. So acetic acid is acting as the acid. It's going to donate its hydrogen. The acetate ion is the conjugate base. They work together. And the water is going to be the conjugate acid. Now, in order to determine the stoichiometry, we have to look at the positioning here. We've got hydroxide. That's a strong base. So now what we need to do is hydroxide with ethanoic acid. That's acetic acid right there. Okay, that one's above the line this time. So acetic acid is sufficiently strong enough to totally react with the hydroxide because it's above that line right there. Okay, there we go. Okay, so we say that it's sufficiently strong enough, it's above the line. Even though it's not a strong acid, we're saying it's sufficiently strong enough to react with the hydroxide to donate all of its hydrogens. There we go. So it's going to be stoichiometric. Every last one of those acetic acids now, the hydroxide is strong enough now to pull every one of those hydrogens off. Every single last one of them's coming off. That's what this means. In this reaction over here, some of them are coming off, right? This is not strong enough. This guy really doesn't want to give up its hydrogen. Even though this is a strong base, this guy really doesn't want to give up its hydrogens. He'll give up some of them, but not all of them, right? And that's what this is representing. Many of these are coming off, but a few are staying on. Okay, there we go. Here's a few extra problems you can try. And again, if you want to try some of these and work them out and see if you can get them to go, great. You can drop me a line in the discussion postings. Throw some of these at your online tutors, some of the ones you can't get, or throw them at your online tutor and see if you got them done right. And check out some of the online content we have here. The old public exams are great. See what types of questions they ask on this. And don't forget we have public exam learning outcomes done on the last 4 public exams that were issued. So go have a look at them. And just one quick review item. Weak acids stay as they are. They do not ionize. The strong acids, they're 100% ionized, but they don't exist like that. Every single last one of these strong acids here is going to behave as H3O+. Okay, there we go. So again, don't forget to use our online resources, our online tutors, online content, and the Department of Education public exams. Lots of good stuff there. Okay, see ya.